up for a question answer section. So next we will have the contributed talk section from 2 to 3. So first talk will be from Tamas Matutska. He's a research scientist from AI Motive, and he will be talking about the AI Motive dataset, a multimodal dataset for robust autonomous driving with long-range perception. Yep, please take away.
Thank you. Okay, hello everyone. And thank you for the introduction. So I'm going to talk about our dataset, which can be used for training robust long-range perception systems. And this is the outline of my presentation. So first I'm going to talk about the problem, what we are going to solve, and the motivation, and then I'm going to describe our dataset. And finally, I'm going to talk about some experiments which is used for validating the usefulness of our dataset. So the autonomous driving is getting to be used in the real world, especially there are several systems which has been deployed onto the cars which are in productions. So for example, let's consider L2 plus highway and highway assistant and address to address system. This is provided, for example, by Tesla. And there is another recently released system which is a highway traffic jam assistant, and it's been released by Mercedes. And these systems are not fully autonomous, so that means that steering wheel has to be held by the drivers, but they are still getting some popularity. Another more advanced system is the L3 highway chauffeur application, which can be used for, actually it can operate high speed, so up to 130 kilometers per hour, and it's able to perform sophisticated maneuvers such as unsupervised lane changing. This system is currently not available on the roads, but there are several companies which are working on that, including AI Motive as a subsidiary of Stellantis. So that's one of what we are working on. And these systems have the common property that they have to be able to detect objects in the far range region in order to provide and in order to enable them to create useful and meaningful maneuvers. And nowadays there are several publicly available datasets which can be used for training neural networks, which is really good because it facilitates the research. However, we have identified several issues which prevents one to use those datasets for training long-range perception and prediction systems. And one of the issues is that the majority of the datasets focuses mostly on urban environment, which means that there is no annotation in the far-range region. So beyond 75 meters, it's usually not annotated. That's not good for long-range perception. And another issue, what we found that even if these datasets provide some multimodal sensor data, it's usually camera and LiDAR, and we saw that LiDAR has some problem in adverse weather, so it was demonstrated by the previous presenters as well, and they underutilized the easily available sensors in the cars, so which are cheap. So let's say the radars are in the cars, and they are better in adverse weather than the LiDAR, and it could be utilized for long-range perception. Okay, so this table collects some datasets and some most popular datasets, and it shows it shows our dataset as well, and it shows the combination why our dataset is beneficial over the other one dataset. So our dataset has a long-range detection, and we're using different data. We're using radars as well, and we recorded our data, the majority of the data on highway environment. So, as I mentioned, we collected our data in two different continents and in 3 different countries in order to provide some diversity in different lighting environment and different seasons and different weather conditions. And regarding the ground truth generation, we used 2 methods. So for the training split, we utilized our automatic annotation pipeline. So this is what my team does, and we developed that. First, we are using LiDAR measurements for the automatic annotation, and we can aggregate a point cloud for an entire 15-second long sequence. This is one input. And in addition, we have a multimodal neural network, which is predicting 3D bounding boxes for the objects. And the output of that neural network is used by the automatic annotation pipeline as input, as object proposals. And since our system is offline, so we can use non-causal tracking, which means we know not only the past, but the future as well, so we can track the data in both directions in time. So it can help to collect the tracks. And if we have object tracks for the object proposals, then we can collect the point cloud across different frames. And because that means that we have several views from the point clouds for corresponding for our object, we can build a pretty accurate object model for that, for each proposals. And if we have built this object model, then we can fit a cuboid on it, and we can assign a unique track ID. So in this way, our dataset can be used for tracking and object detection as well. And since it's an automatic annotated system, of course, it has to be validated manually. So therefore, we have hired manual laborers, and they check the quality of our data in order to ensure that only the good annotation is contained by the dataset. And that was for the training split. And for the validation split, we used a conventional solution. We just hired manual laborers, and they annotated by hand the data, and they used the camera and the LiDAR sensors as well. Okay, so this is the sensor layout. So we used a spinning LiDAR, 4 cameras, 2 pinholes in the front and the back, and 2 fisheye cameras in the side. So that means there are some overlapping areas between the cameras. And of course, we are using long-range radars in the front and in the back of the car. And the sensor data is synchronized, so everything can be used. So for one frame, we have the synchronized timestamps for all sensors. So it can be used for multimodal models. Okay, so these are the main characteristics of our dataset. So it contains 176 scenes and over 25K annotated frames, over 40K 3D bounding boxes. Among those, more than 50K is beyond 100 meters in front and back of the car. And this is a sample video. So it's created, sorry. So it's created by the automatic annotation pipeline without any manual intervention, so it's fully automated. This is in a suburban area, and next is gonna be in the highway during the night. Okay, so if we had the data set, so we wanted to create some and perform some experiments, and we trained several uni and multimodal models. For the LiDAR-only model, we used the voxelnet. For the camera-only baseline, we used the BEV depth. For multimodal baseline, we used the BEV fusion. And since BEV fusion doesn't use radar originally, we developed a really simple sensor fusion method. So actually, we just merge the 3D point cloud of the radar into the LiDAR point cloud, and then it can be fed by the voxelnet. And we conducted several experiments, but I wanted to highlight one, so which validates the feasibility of the sensor fusion method. And so we trained a LiDAR-only model, and we trained a LiDAR plus radar model using the sensor fusion method. And because we wanted to know whether the models are able to detect objects in the far range region, we evaluated our models in the far range, which means beyond 75 meters in front of the car and in back of the car. And as it can be seen on the figures, the orange curve is above, in the most cases, than the blue, which means that sensor fusion model works better, especially in the rain. So our raining split has very heavy rains, where the LiDAR is not really able to see properly, and the radar can go through the raindrops, so that's the reason why it works better. So to conclude, we released a multimodal dataset which can be used for long-range perception, and we chose the 3D object detection as the baseline task. However, the dataset can be used for different tasks as well, because it has track IDs, so we can use that for end-to-end tracking or joint perception and motion predictions. For example, we are planning to try the FIRE, which was mentioned in the previous presentation. And also we released several unimodal and multimodal baselines and developed the simple fusion method and the dataset and the training framework. The pre-trained models are available on the GitHub link, and you can read the paper for more details by scanning the QR code. Thank you.
Okay, any questions for the speaker?
Okay, so I have a question. So you noted you mentioned that your training data and the validation data or testing data, you automatically annotated your training data, but you manually label your testing data. So and you have some baselines for your benchmark. Do you have some insights about how large is the domain shift between your training and test data?
Yeah, I checked manually the data set, so there isn't a huge domain gap. Maybe the manually annotated has a bit longer range sometimes, because you can see the annotators were able to see the really faraway objects on the LiDAR point cloud. But beside that, I didn't find any huge difference because the automatically annotated data has been manually checked. So there might be some errors, so I can't claim that it's 100% accurate, but we try to filter out every bad data, and in terms of distribution shift, there isn't any difference. So it's the same, so from the same operation domain design.
Okay, cool. Could you elaborate more about the size of your data set?
Yeah, so it has more than 25K annotated LiDAR frames, and it has the 4 cameras. Sometimes it's 5, it depends on, because we use 3 different cars, and one of the cars has stereo camera and the radars. So it's not huge, but it still can be used for training models.
Okay, thank you.
At least based on the baseline models results.
Great, let's thank the speaker again. So next up, we have Chenfeng Xu from UC Berkeley on time will tell new outlooks and the baseline for temporal multi-view 3D object detection. So Chenfeng will present remotely.
Hi everyone, thank you for coming to our presentation. My name is Chenfeng Xu, and I will be presenting our paper, Time Will Tell, New Outlooks and Baseline for Temporal Multi-View 3D Object Detection. We address the task of 3D detection from camera images in the autonomous driving scenario. Recently, there has been a surge of works leveraging images from past timestamps. Using these previous frames is critical for better depth estimation, which is the main bottleneck of camera-only pipelines. While existing methods have developed a number of different temporal fusion methods that demonstrate limited improvement from leveraging past frames, we found that this is due to the low matching resolution and the suboptimal multi-view setup produced by limited history usage. Most methods limit their temporal fusion to just a couple frames in a short 2 or 3 second window, discarding the majority of past observations. We analyze this issue by first drawing a connection between temporal 3D object detection and multi-view stereo. In multi-view stereo, the model predicts the likelihood that a candidate location is occupied by anything, while temporal 3D detection models predicts whether the location is occupied by a certain object. At their core, both methods have the same goal. Given a candidate 3D location, they both consider how the location is captured in multiple 2D views to determine whether something of interest is there. Following this connection, we can break down the various components of multi-view stereo and temporal camera-only 3D detection methods under a single framework of multi-view stereo. This includes what 3D candidate locations are considered, how these XYZ point sampled features from the image, what past images are used, and how the final prediction is made. To quantify the quality of multi-view temporal depth estimation possible, we define localization potential at 3D location as the magnitude of the change in the source view projection induced by a change in the depth of the reference view. Intuitively, a larger localization potential calls depth hypothesis for reference view pixel to project further apart, giving them more distinct source view features. Then, the correct depth hypothesis with a stronger match with the reference view feature can more easily suppress the incorrect depth hypothesis with clearly unrelated features. This allows for more accurate depth estimation. And the natural question is, what path source frames is optimal for maximizing the localization potential in the current reference frames? Here, we visualize the time steps between the source and reference view that maximize localization potential. We find that the optimal time differences vary significantly over different pixels, depths, cameras, and equal motion. As such, it is necessary to utilize many time steps of a long history for each pixel and depths to have access a setup that maximizes its localization potential. Another factor that impacts localization potential is image resolution. If a depth change in the reference view induces sub-pixel change in the source view, it is more difficult to determine the correct depth through multi-view matching. As such, downsampling image features by 4 times decrease localization potential by a factor of 4 as well. However, we find that compared to using a single source view as existing methods do, leverage a denser and longer history improves localization potential by far more than a factor of 4. Furthermore, the localization potential with less than a factor of 4 improvements are generally close steps of which molecular depth estimation has good performance and localization potential is already high enough. Therefore, our analysis shows that aggregating more time steps can compensate for lower image resolution, maintaining high efficiency with same localization potential as high-resolution feature matching. Based on our analysis, we propose solo fusion, which maintains high efficiency while maximizing localization potential by balancing image resolution and temporal aggregation. More specifically, solo fusion has 2 main streams: the LSS-based 3D detection temporal stereo module leveraging coarse 16 times downsampled features with a long history, and a multi-view-based depth prediction methods that use high-resolution 4 times features with a short history. At a high level, the coarse long history streams align 60 path bird-eye frames, each at 2 Hz, and the fine-grained short history stream performs multi-view stereo matching with depth hypothesis guided by molecular depth predictions. By leveraging design principles derived from our multi-view stereo analysis, solo fusion achieves new state-of-the-art in various settings. Additional results and details can be found in the main paper. Operating both the short and long-term fusion, we find that although the high-resolution short-term module impacts runtime, the localization matrix MATE is dramatically improved. Low-resolution long-term fusion also improves performance, and modules are complementary, resulting in better detection when used together. We previously showed that extensive temporal fusion can compensate for lower resolution in terms of localization potential. We verify this by comparing half-resolution solo fusion, designed to offset low resolution with long-term temporal fusion, while full-resolution bird-eye depths, which use short-term temporal fusion. While bird-eye depths demonstrates stronger performance, solo fusion is able to match its performance with low resolution and high FPS. Thank you for listening, and we hope that our work can serve as an efficient and stronger baseline for temporal 3D detection, and I hope that it can inspire research in the future. Thank you.
Hello? Okay. So next up, we have Zhuo Xiaochen from University of Queensland presenting Exploring Active 3D Object Detection from a Generalization Perspective.
Hey, thank you. Hi, everyone. I'm very happy to have a chance to present our research work exploring active 3D object detection from a generalization perspective, which was published in ICLR23. And this work is from the University of Queensland. I'm the presenter, Zhuo Xiaochen. Let's start with the research background. Deep neural network-based 3D detectors require training on benchmark datasets with a large number of human annotations. So when we label a single bounding box, we need to consider 7 degrees of freedom, which is the position, size, and orientation. So it can take more than 100 seconds for an annotator to label each object. And let's have a look at how many labeled bounding boxes in widely used benchmark datasets. For the Lyft L5 and the New Sense dataset, there are more than 1 million human-labeled bounding boxes. And for the Waymo open dataset, which is larger, it has more than 10 million labeled bounding boxes. So labeling 3D datasets is actually very expensive and time-consuming. It's very necessary to come up with a way to resolve the annotation burden and make the 3D object detection more efficiently. And our solution is to use active learning. AL attempts to maximize a model performance gain while annotating the fused samples. And initially, we will have a small size of label data, and the machine learning model will learn from the label data, and then we will have a very large unlabeled data pool. And the goal of active learning is to design a sampling strategy that can select very useful and informative data from the label pool for human to annotate. And the label data will be added into the label set and then retrain the model. So that is the active learning loop. And recently, some active learning methods has been investigated for object detection tasks. And this work, which was published in ICCV 2021, it replaced the conventional localization and classification ahead by mixture density networks. So that is the Gaussian mixed model. Because GMM is a probabilistic model, so the parameters of GMM can be used to estimate the aleatoric and epistemic uncertainties for both localization and classification heads and for each object. And finally, they select the images with the highest top K estimated uncertainty. And there are some limitations for this work. First, it only considers the uncertainty and ignores the diversity of the selected objects. So they will probably select some objects with very similar pattern. And in their experiments, they use incorrect annotation unit, which is the number of annotated images, because with their method, they will favor images with more objects because of the higher chance to contain uncertain objects. Then more clicks are required for annotating. So in our work, we revisit the annotation unit to the correct one, which is the number of annotated bounding boxes. And the third limitation is that it is infeasible for extension to heavy 3D object detection tasks because the GMM has involved more parameters and increase the training and the inference time. And in our work, we explore some methods based on active learning for 3D object detection. And we propose 3 active selection criteria, the label consensus, feature representativeness, and geometric balance. And for the label consensus, we acquire objects with diverse classes to alleviate the class imbalance. And for the feature representativeness, we acquire point clouds that are both diverse and uncertain in the latent space there to seek the uniqueness. And for the geometric balance, we acquire objects with diverse row geometrical characteristics to reduce the geometrical redundancy. Okay, let's go through each of the stage. And for the label consensus, we first compute the label entropy for each point cloud. And we have an example on the right-hand side. For the upper point clouds, this point cloud contains the objects with diverse classes, and the label entropy is computed as the 1.5. And for the lower point cloud, all the objects are car, so the label entropy is just 0. So which means higher label entropy, less label redundancy. So select point cloud with the highest K1 label entropy. And in the stage 2, we first compute the hypothetical labels by averaging the regression results on the different dropout masks. So with the hypothetical labels, we can compute the loss and then use the back propagation to get a gradient. And in the gradient space, we can just do the K2 bandwidth problem to find K2 bandwidth point cloud that cover the unique knowledge. And in the stage 3, we fit all the box densities from the selected point clouds to the kernel density estimation, the KDE. And our goal is to find NR point clouds such that the KL divergence between the KDE and the uniform distribution is minimized. And we apply the greedy search to find these point clouds. And the final search point clouds will have the balanced geometric characteristics. So for example, on the right-hand side, the selected point cloud will contain both sparse objects and dense objects. And this is our framework of the proposed CRB. Initially, the DU here is the unlabeled pool. It will be passed into the first stage consensus. We select K1 point clouds. And in the stage 2, we select K2 point clouds. And in the last stage, we select NR point clouds. And finally, these NR point clouds are passed into this active learning loop. Let's have a look at the experiment results. We first have some plots to show the performance with increasing annotation cost. As you can see, the annotation cost is measured as the number of selected bounding boxes. And the proposed method, CRB, is represented by the pink line. So it consistently achieves the best result with the least annotation cost. And we also compare the performance with only 1% labeled bounding boxes. And CRB can produce significant performance boost in all classes, especially in real classes, which are the pedestrian and cyclist. We also did some qualitative analysis. We visualized some detected objects, but model that's trained with different AO strategies. So with the random sampling on the left-hand side, we can see there are some incorrectly detected objects and some misdetected objects. But with the proposed CRB on the right-hand side, the detection result is much better, and it can assign higher confidence in correctly detected object, for example, the very front pedestrian here. So that's all about the presentation. Thanks for listening. And our code is made publicly available through this link. Thank you.
Thank you, Zhou Xiao, for the great talk. So we can have the audience to have questions since Zhou Xiao is online. Any questions? So maybe I can start with one question. So in your experiments, when you have partially labeled scenes, do you have to do extra treatment for the input so that it doesn't predict for the negative regions that haven't been labeled?
For the initially labeled datasets, actually all the objects are labeled in the initially point cloud. So all the objects are labeled in the point cloud, so there will be no missing objects.
So are you choosing the entire point cloud instead of the each object?
Yeah. Actually, we choose the, for example, we choose 100 point clouds from the unlabeled pool, and we label all the objects in the 100 point cloud.
Thanks. Any other questions from our audience? Well, let's thank Zhou Xiao again for his talk. Okay, next up we have Renjie Chen. He's PhD from the University of Hong Kong. He will be presenting CO3, Cooperative Unsupervised 3D Representation Learning for Autonomous Driving. Let's bring Renjie online.
Okay, so can you see my screen? Oh, okay. So, okay. Thank you. So hello everyone, and I'm happy to introduce our work on the cooperative and supervised 3D representation learning for autonomous driving. And this work is accepted at ICLR 2023. And I'm Renjie Chen, a second-year PhD student from the University of Hong Kong. So LiDAR is one of the most reliable sensors in autonomous driving, and it is time and energy consuming to label this 3D data. So the unsupervised 3D representation learning, which utilizes the unlabeled 3D data to pre-train the 3D backbone for better downstream performance tasks, with better downstream performance, is very promising. And this is a pipeline for the unsupervised 3D representation learning. We first pre-train only once with different methods for the 3D backbone, and then use the pre-trained weight to initialize different downstream architectures on different datasets to achieve performance gain. Unsupervised contrastive learning have achieved great successes in computer vision and multimodal domain. The basic idea of contrastive learning is to pull together the features of the same instance in the feature space while pushing the features of different instances apart. So we can have a look at this left figure. In the feature space, the features of the two augmentations of the same image, the puppy, is pulled together, while the features of the other instance are pushed farther away from it. And the most important part in contrastive learning is view building. Views of the same instance should differ enough to help the encoder learn more information, while maintaining enough common semantic information to help identify this view as positive pairs. The right figure shows the relationship between the transfer performance and the mutual information shared by the two views. And there are some works that applies the contrastive learning to 3D schemes. The pioneering work is point contrast. It first reconstructs the whole scheme and captured partial point clouds from different poses to build views for contrastive learning. And follow-up works for indoor scheme point clouds like P4 contrast and contrastive scheme context also require the whole scheme reconstruction. The assumption for scheme reconstruction is that the scheme should be static and have limited scales. And however, autonomous driving cars are deployed in the large scale and dynamic outdoor scheme. And this makes it unable to directly transfer this matter to the autonomous driving application. And there are also some works for outdoor scheme LiDAR point clouds. For GCC 3D and proposal contrast, they applied augmentation of point clouds, including translation, rotation, scaling, and random dropout to build views. However, these augmentations can be simply implemented as a linear transformation of the point cloud. So views built in this way are too similar and bring little improvement, especially when downstream the pre-trained weight to the other dataset. And the first two figure here shows an example for this kind of view building. And for STRL, point clouds at different timestamps are utilized as positive pairs, and as shown in the first and the third figure here. But the outdoor scheme are dynamic, and we have no idea how other traffic participants are moving. So it would be very hard for us to find correct positive pair in these views. So these views built in this way share little common semantic information. Thus, to overcome this limitation, we propose our CO3 to utilize the cooperative dataset for unsupervised representation learning. And the vehicle to everything, that is V2X community, is developing rapidly, and dataset from simulation to real skins are collected. In our work, we utilize a recently published vehicle to infrastructure dataset called their V2X to build views for contrastive learning. As shown in these figures, two LiDARs are set at the infrastructure side and vehicle side respectively, and the LiDAR, the sensor data are collected at the same timestamp. So we have the LiDAR information from different sites for the same scheme. So views built in this way would share enough common semantic information, but meanwhile they are different. They are different because they are captured at different poses. And this is an overview of our proposed framework. So firstly, the vehicle and infrastructure side point cloud are fused together using transformation metric between the two sensors. And the vehicle side point cloud and fusion point cloud are processed by the shared 3D backbone. And we obtained voxel level features for vehicle side point cloud and fusion side point cloud. And then we applied two pre-training goals. That is the cooperative contrastive loss and the contextual shift prediction loss to pre-train the 3D backbone. The first loss is cooperative contrastive loss, and the features of the both sides are first projected into a common feature space by the contrastive head consisted of the multi-layer perceptron, and then we applied L2 normalization on them. Then we randomly sampled N1 pair of points and applied the NC loss, the noise contrastive estimation loss to them. Then we analyzed the task relevant information in the learned representation Z and noticed that pure contrastive learning would make the learned representation lack of the task relevant information. So we denote the information contained in view 1, view 2, and task T as 3 ellipses here with overlapped. And then the orange part here denotes the information contained in the learned representation Z. While pure contrastive learning pull the learned representation Z more close to the intersection part of view 1 and view 2, it also decreased the shared information between the learned representation Z and the task T, which is colored in green here. So to introduce more task relevant information here, one way is to increase the mutual information between the learned representation Z and the view 1. However, it is extremely difficult for a voxel level or point level feature to reconstruct the whole skin. So we propose to reconstruct the local point distribution using the point level or voxel level representation. And this is our second pre-training goal, the contextual shape prediction loss. We first divide the neighborhood of the query point, which is marked as black here, into n bins. And for the example here, n equals to a. And then we compute the number of points in each bin and construct a probability distribution with the number of points in each bin. Then we predict this local points distribution using the features of this queried point. And these are experiment results of our methods. The first experiment is for the 3D object detection on one dataset. It can be found that our method consistently improve the performance of different detectors and achieve the best performance among all the initialization methods. And notably, we improved center point on one dataset for 2.5 MAP. The second experiment is semantic segmentation on leader point cloud. It can be found that initialized by our CO3, the cylinder 3D achieved 3.54 MIOU improvement. And when we look into the detailed categories, it can be found that for truck, construction vehicle, trailer, bicycle, and motorcycle, and for these categories, our CO3 improved the performance by a large margin. And this is very important because accurate segmentation and can help the downstream decision-making process. And finally, these are some visualization of the detection results when pre-trained by CO3 and the point contrast. For case 1 and case 2, it can be found that when pre-trained by CO3, the detectors can make a more accurate prediction. And for case 3 and case 4, it can be found that for some extremely hard examples, which only where we can only have very few points for the object, when pre-trained by CO3, the detector are able to detect the disease object, but when pre-trained by the other methods, the detector failed to detect this object. Yeah, and that's all. Thank you for your listening.
Okay, thank you. Any question from the audience here? So when you train the CO3, do you find more agents, cooperative agents, yields better results?
Yeah, currently we only use the infrastructure side and vehicle side, and we are going to use a more recently published vehicle-to-vehicle dataset. But now we don't have any conclusion on more agents. What would the result be with more agents? But I think that it would be the result. The performance improvement will be larger if we can incorporate more agents.
The speaker again, since we're running out of time.
So
next up, we have Lingdong Kong, who's a PhD at National University of Singapore. His talk is going to be on the topic of benchmarking 3D perception robustness to common corruptions and sensor failure.
Hello guys, can you see my screen? Okay, great. Hello everyone, my name is Lingdong. I'm here to introduce our work, benchmarking 3D perception robustness to common corruptions and sensor failure. And first, the 3D perception is an important task for the autonomous driving system. And here the 3D, which we mean the point cloud collected by the LiDAR sensors. And different kind of 3D perception tasks in these scenarios have been proposed. For example, the LiDAR semantic and the panoptic segmentation, the 3D object detection, and most recently, the 4D panoptic segmentations. And here, why are we using LiDAR sensors for doing the perception task? The main reasons are the following. The first is that the LiDAR sensors can provide accurate depth sensings and also the robust sensing at low light conditions. And also it can directly give us the 3D positional information of the surrounding environments. And in this work, we are considering the robustness of the 3D perception task. This is mainly due to because of the autonomous driving car is actually operating on the in the real world environments, which is diverse and complex. For example, there are multiple weather conditions with different lightnings conditions in the real world environments. For example, the snowy weathers on the left, and also there are kind of the cases that, for example, the raining and the dark lightning conditions on the right. Those different examples are actually only partially considered, or even without considered by the current LiDAR perception datasets. So here we introduce the robust 3D benchmark to fill in this gap. These are the key contributions of this work. Here we introduce this benchmark. This is the first systematically designed robustness evaluation suite for the LiDAR-based 3D perception task under the corruptions and sensor failures. And with our benchmark, we include 34 perception models for the LiDAR-based semantic segmentation and object detection task on their robustness against the corruptions. And also based on our observations, we draw in-depth discussions on the recipe of designing robust and reliable 3D perception models. Here, I briefly introduce the taxonomy of this benchmark. We introduce 8 different corruption types, ranging from different conditions like the weathers and the sensor movement and the failures. For example, the foggy weathers is likely to causing the noisy points on top of the vehicle in the air. And also the raining weather is actually causing the background phenomenon, which is actually causing some loss for the ground points. And also the snowy weather is causing the noises in the air as well due to the reflections of the snow particles. There are also the sensor movement problems caused by the motion blurs or the failure cases, which is causing the LiDAR being missing. There is another case that there are, for example, multiple vehicles equipped with LiDAR sensors is presenting in the same scene, and these different kind of sensors might interfere with each other's. And lastly, we consider the incomplete echo scenarios and the cross sensors. The cross sensor is referred to like different sensor setups. For example, the 32, the 64, and 128 different numbers of laser beams for different types of the LiDAR sensors. And it's well known that the 3D perception models is adopting different representations to handling the processing of the LiDAR point clouds. For example, there are like the 2D representations like the range view and also the bird's eye view, which is projecting the point clouds into the plane and use operators like the COM2D to handle this kind of representations during the training. And also there are mostly popularly adopted representations like the cubic voxels and cylinder voxels, which we can use the COM3D or the SPOTSCOM to handle these different representations during the feature learning. And some statistics about our benchmark, we introduce 8 different corruption types, and each with 3 severity levels: the light, moderate, and heavy. And for the datasets, we included 6 different datasets by using the existing popular LiDAR-based perception datasets, for example, the Semantic Kitty, NewScenes, and Waymo Open. And also for the models and algorithms, we included 34 of them, and 22 of them are for LiDAR semantic segmentation, 12 of them are for 3D object detection, and we also consider most recently 3D augmentation techniques. For the metrics of measuring the robustness, we split them into two different categories. The first one is the task-specific accuracy, which is usually depends on the tasks themselves. For example, for LiDAR semantic segmentation, we usually use the mean IOUs to measure the accuracy. And also for the 3D object detections, we use the mean average precision and the nuisance detection scores to measuring the model performance. And for the robustness measurements, we introduced the mean corruption error, which is the error rate across three different severity levels of a models divided by the same errors of the baseline models. And the average corruption error is the mean values across the 8 different corruption types. And similarly, there is a mean resilience rates, which measures the accuracies under the corruptions divided by the clean accuracies. Some main results from our benchmark on these 6 different datasets. Here we show the task-specific accuracies on the horizontal axis and also the MCE and the MR on the vertical axis. We show that there are some notable trends for these benchmarks. For example, for the segmentations on semantic kitties, we show that the model perform better 3D semantic segmentations usually have the lower corruption errors, which means that they are actually more robust. And this is also reflected by the resilience rates. But the trend is actually getting flat. So we're at the risk of being less robust without considering the robustness of the current different perception models. Some key observations from our experimental results. The first one is that we found that the existing 3D detection and segmentation models are vulnerable to real-world corruptions, which means that their accuracies under those different kinds of corruptions are actually much more degraded compared to their clean results. And also the models trained with LiDAR data from different sources. For example, different LiDAR beam numbers is exhibiting the inconsistent sensitivities to different corruption types. And most importantly, representing the LiDAR data as the points, sparse voxel, or the fusion of the point and the voxel is actually the kind of best possible choices for helping the model getting more robust, which is showing in these figures. And also, we also found that the 3D detection and segmentation models is likely to show different sensitivities to the corruption types. For example, the segmentation models is actually more sensitive to the wet ground time, while the detection models, which only focus on the object level perceptions, is actually robust under the raining weathers. And lastly, we found that some recent out-of-context augmentation techniques is helping the models to getting more robust. And also some flexible rasterization strategies, like modifying the fixed voxelization resolutions to a dynamic one, is helping the models to learn more robust features. And lastly, we show some realization results for like different kind of models under the different corruption types. We show them they are actually exhibiting different behaviors under these cases. And also for these detection models, we also observed that their performance is just dropping a lot under the corruptions. And our benchmark is actually available to the public on the GitHub repos, and we built our benchmark upon the detection 3D repository. So if you are interested, please give a start to us and test your models on our benchmarks. Thank you for your attention.
Let's thank Lindong for his talk. Any questions from the audience? So maybe I will ask a question. So have you tried to train your models on these corrupted data, and which model performs the best, either range view or fusion or point cloud models?
Okay. In this work, we didn't try to train the models on the corrupted data because we are mainly focusing on the out of distribution cases, which means that the evaluation distribution is shifted from the training distribution. And all the models we benchmarked are actually trained on clean data sets and tested on our corrupted data set. So in this way, the results can reflect their robustness, their out of distribution robustness against their corruptions. So yes, but as you said, the training on those corrupted data sets is actually helping the model to get more robust because it's likely to increase the diversity of the training distributions since we are involving more kinds of data during the training. So I think this is a viable in the robustness and where is in our work. Thanks.
All right, our last contributed talk is from Young-Seok Kim. He's a PhD from KAIST. He will be presenting his work on CRN, Camera Radar Net for accurate, robust, efficient 3D perception.
Hi, thank you for interesting. Can you see my screen share? Okay then. Let me start the presentation. So, hi, I'm Young-Seok Kim from KAIST, and I'm happy to share my work today. The title of the presentation is CRN, Camera Radar Net for Accurate, Robust, Efficient 3D Perception. And it seems that we are running out of time, so I will try my best to keep the presentation time. So I'm going to start the presentation with the background and motivation of camera radar fusion. So why do we choose camera and radar instead of using LiDAR? So currently, the LiDAR is most preferred sensors for autonomous driving thanks to its dense and precise data. However, the high price and mechanical parts of LiDAR is not suitable for commercial vehicles. On the other hand, camera and radar are already widely used in ADAS thanks to their many suitable properties for mass production. But the driving environment of ADAS is very limited to non-complex environments such as highway. So in this work, we aim to achieve LiDAR level performance with low-cost camera and radar sensors, and we believe it will have a great impact on vehicle intelligence. But the camera and radar fusion is not easy. As can be seen on the left, the camera and radar have very complementary properties. And more specifically, radar has advantage in long-range measurement, but its angular resolution is very limited. And on the other hand, the camera provides dense angular resolution, but the image pixel itself does not provide distance information. And because of the limitation of each sensor is very clear, if we process single sensors individually and fuse the information at the later stage, it will not be able to overcome the limitation of each sensor. However, camera and radar have a great potential if we could take only advantages of each sensors without their drawbacks. So to achieve this, we developed an effective fusion network to handle these complementary properties. In molecular 3D perception, we have to transform the information in 2D image space into the 3D space, but the estimating depths from single sensor is challenging and an ill-posed problem. And moreover, the performance of the molecular depth significantly drops on this kind of moving object or small objects, which is very critical in driving environments. And we want to improve it by using radar. But there are some technical challenges when using radar caused by the unique properties of radar. First, the radar measurements are very sparse and ambiguous, so not every radar point's radar measurements are beneficial for the detection. And moreover, Pixel-to-pixel mapping is not available in radar compared to LiDAR because there are multipath problem or there are no height information from radar, and it makes the camera radar fusion challenging. And to this end, we have to treat these radar points in very adaptive manner. And the goal of the proposed method is to generate a reliable bird's-eye view feature map that has rich semantic information from camera and accurate spatial information from radar. So we can utilize this bird's-eye view feature map obtained by Fusion for multiple downstream tasks, including 3D perception, tracking, and bird's-eye view segmentation. And in summary, our method achieves LiDAR-level performance on 3D detection task, and it maintains robust performance in sensor failure cases. And finally, it can be run in real time with that TensorRT kind of optimization. And our first key module is radar-assisted view transformation. View transformation is a module to transform these 2D image features into 3D using the depth distribution, but the problem is that the depth estimated by the camera becomes less accurate as object becomes far, as can be seen here. And to improve the dense but less accurate depth distribution, we attempt to use accurate but sparse and ambiguous radar points cloud. However, directly using radar point cloud is almost impossible because of the technical challenges that I mentioned. Therefore, we first voxelize the radar point cloud into a pillar-shaped grid and predict the occupancy of the grid. And in this way, we can effectively overcome the problem of radar, which is radar point cloud is noisy and radar has no height information. And after obtaining radar occupancy, we use both depth distribution and occupancy to transform these 2D image context features into the 3D space. And after transforming the image feature map into the bird's-eye view space, and we further aggregate radar feature map in bird's-eye view space to handle the spatial misalignment between two features and to fuse complementary information from two sensors. In this example, white and blue circle highlights the cases that the objects are not detected by camera because of the occlusion. And this red circle highlights the case the radar suffers from noises from the wall. And our fusion modules aim to aggregate multimodal features in an adaptive manner utilizing this attention mechanism. And this attention module takes camera and radar features as key and value and adaptively fuses two modalities. As a result, we can see the feature map by Fusion has more rich context feature at a more accurate position. And this video shows the comparison between camera only and camera plus radar, which is ours, and LiDAR only method. As can be seen in the video, ours have more accurate localization at a faraway object. And moreover, camera radar fusion shows more robust performance in rainy scenarios compared to the LiDAR. And finally, we find that the localization becomes more robust under low lighting condition compared to the camera-only method suffers from the localization error. As shown in the left, the proposed method has a good speed and performance trade-off, and it ranked the first place on using 3D detection benchmark among camera and camera radar fusion methods. And also, we validated our method on tracking and segmentation tasks by replacing the detection head with the segmentation head. And we confirmed that the proposed camera and radar feature map obtained by Fusion can be generalized in many downstream tasks for autonomous driving. And we conducted several observation studies to verify the effectiveness of our method. First, we increased the perception range from 50 to 100 meters, and compared to the LiDAR method, our camera radar fusion can have better performance at longer distance with a faster inference time. And moreover, compared to the camera-only method, our fusion module requires only a marginal computational cost to significantly improve the performance on this scene. And we also analyzed the robustness by randomly dropping the camera and radar sensor inputs. And compared to the naive fusion method using feature concatenation, our attention-based fusion shows more robust performance in these sensor failure cases. So I want to conclude the presentation with two takeaways for camera and radar fusion. The first one is that understanding sensor characteristics is very important in camera and radar cases. And the other is that we need an adaptive mechanism to fully exploit camera and radar. I hope our paper will inspire future research on camera and radar fusion. And thank you for interesting and check out my paper if you're interested in details. Thank you.
Thank you, Yang-seok. So since we're already 10 minutes over, we'll not have the QA section. Thank you all for attending, and we will have 20 minutes of a break, and we'll reconvene at 3:30 p.m. for another 2 invited talks and a panel discussion. Thank you.